Hello students, welcome to Inside Physics. This is Srinivas. Today we are going to discuss about Seebeck effect in thermoelectricity. The concept thermoelectricity is a branch of solid state technology. The term itself says thermoelectricity. The electricity caused by the heat effect, that means the difference in temperature of a material. So here we discuss about the Seebeck effect in the branch of thermoelectricity. Before going to the what is Seebeck effect, we will discuss some details about thermoelectricity. It was discovered long back, I think about 100 years back. But the applications of thermoelectricity are just being invented in recent times. It has so many applications, and because of this applications of thermoelectricity, there are so many uses like measuring temperatures, generating electricity, and cooling objects and heating of the objects also. Okay, what is thermoelectricity? See, the electricity, the potential difference causes some heating effect in a body, in a material. And in the reverse, if you maintain some temperature difference across a material or across two junctions, so a potential difference, that means a current flow, is generated in that material or across the two junctions because of the thermoelectric EMF generated because of the temperature difference. Okay, see, this is what the Seebeck effect says. The temperature difference is the cause of electricity in a material. So it may not be in higher voltage. The potential difference will be in microvolts, a small voltage. Okay, and one more thing is there in thermoelectricity is Joule heating effect. Joule heating effect says that whenever a resistive material like a metal is applied to a heating effect, so a potential difference will be generated in that material. Or if you apply a potential difference across a resistive material like metal, so some heat will be generated in the material because of that potential difference across the 2 points in a conductor or material. This is called Joule heating effect. So this is also somewhat related to thermoelectricity, but actually it was not considered as a branch of thermoelectricity, the Joule heating effect, because it is not reversible. It is not a reversible effect. That means if you get some voltage across the material by applying some heat, and it cannot be reversed, and the heat that is produced by applying some voltage across the material will not be reversed. It is not the same, the path of the generating voltage by applying heat effect or getting some heat by applying some potential difference across the material are not do not follow the same path. So it is not a reversible one. That's why the Joule heating effect is neglected with thermoelectricity. Okay, next, see the Seebeck effect. The Seebeck effect actually is considered as a thermoelectric EMF. Thermoelectric EMF generated between the two junctions of two materials. Suppose if you consider two materials or metals, okay, connected. Okay, so this AB is two junctions at a temperature difference of T1 and T2. So this is another material. This is another material. This AB is one material and this is a second material connected at the junctions A and B. And across this one, if you measure some voltage, there will be a voltage potential difference across this closed loop in we will get in some microvolts. So this both are having temperature difference. T1 and T2 are the temperatures at junction A and B. So in this way, Seebeck effect says that a thermoelectric EMF is developed across two junctions connected by two different metals because of the temperature difference across the junctions. So this thermoelectric EMF causes an electric current in a closed loop. If it forms, these two material forms a closed loop, then the electric thermoelectric EMF developed between the two junctions causes an electric current, continuous electric current in the loop. So this is what the Seebeck effect says. Okay. So Seebeck effect and the Peltier effect and then the Thomson effect. These are the three heating and electricity effects in thermoelectricity. First we will discuss what is Seebeck effect here and the Seebeck coefficient. Okay. Thomson later given a mathematical and theoretical representation of Seebeck and Peltier effect, and he proved the relation between Seebeck and Peltier effect, and he also by then because of the relation between Seebeck and Peltier effect, he also proved the existence of Thomson effect. Okay, we know that these Seebeck and Peltier effects are reversible, just unlike Joule heating effect. Because these are reversible, we can use these for so many applications. Okay, see, just like I have already told you, for generating electricity, measuring temperature, and cooling the objects, and also heating the objects. Here, the direction of cooling or heating, see, the direction, that means the direction of cooling or heating across a material or conductor depends upon sign the sign convention of the potential difference. Suppose if you apply a potential difference and the electric charge, the charge carriers will move from here to here. So because of this sign convention of the potential difference, we can say the direction of heating or cooling. Generally, in Seebeck effect, we can say that the hot junction at the hot junction, the electrons, the charge carriers will move from the hot junction to cold junction. If you say this is hot junction T1 greater than T2, suppose the temperature is greater than T2, the junction A is at a higher temperature. The electrons, the charge carriers will move from T1 to T2. Okay, so in this process they will leave the stable nuclei at this hot junction and the electrons, the charge carriers will move towards this junction T2. So the positive and negative charge differences create the necessary thermoelectric EMF and create some potential difference, thereby creating some current effect in this loop. This is how we can say the sign convention of the potential difference. That means if the current is flowing in this direction, so we can say that the charge carriers will be moving in this direction. So the charge carriers obviously move from hot junction to cold junction. By this sign convention, we can say this is a hot junction, this is a cold junction. So, in this way, the Seebeck effect can be explained on the basis of cold and hot junction, and the charge carriers are moving from hot junction to cold junction. In this process, they will leave the stable nucleus at their position where they have left from, and the nucleus, the positive and the negative charge, the charge carriers are accumulated here. So the difference of potential creates the necessary thermoelectric EMF. Okay, so here if you see, the Seebeck effect is not only for metals, it is also applicable for semiconductors also, and it is not only for this junction type of loops, it is also applicable for single conductors. In single conductors, there will be an open loop voltage. We call it as open loop voltage. If two materials are formed a closed loop, then this is called a closed loop current. Okay. So here the Seebeck effect is all about the temperature difference, and thereby the thermoelectric EMF is generated across the material. So after that, we will see some basic concept on the origin of thermoelectric EMF. Origin means from where the EMF is created. From where the EMF is created. Origin of thermoelectric EMF. Okay. So the origin means, actually we have already discussed the potential gradient. That means gradient means difference. So the potential difference across the 2 points of a conductor, 2 points of a conductor will actually create the thermo EMF. We have already discussed that one. So after, if you consider A as a hot junction, B as a cold junction, so the thermo EMF will be created between these two because of the potential, because of the temperature difference. And when the charge carriers are moving from this junction to this junction, why they move from this junction to this junction means, see, at hot junction they will receive some energy, and they will increase their kinetic energy because of the excited states they will move into, because of the energy receiving at the hot junction. They want to get stabilized by coming into the lower states of energy. So in this way they will move, they will try to reach the cold junction, and they will try to come to the lower levels of excited states. In that process, the charge carriers will move from here to here. So here, if a thermal equilibrium arrives, suppose this hot junction and cold junction after some time will be becoming a thermal equilibrium. That means the temperature difference will be ceased. When the temperature difference is ceased, the charge carriers will be stopping, and they will not move from here to here. Okay. So if the temperature difference is maintained only, then only the charge carrier, the potential difference will be there in the conductor. That means if you want to get the higher voltage or potential difference across the element or material, then you need to increase the heat. You need to give more heat. You have to maintain a potential gradient, the difference between the 2 points, the temperature difference. You should maintain a higher temperature difference to get some higher voltage. So actually, this is, it will be in just a micro volts. It will be in microvolts, not more than that. Okay. So in this process, if you want to generate more power by getting more potential difference, what we have to do? We have to give the heat so that the two junctions are maintained the temperature at a temperature difference of high temperature difference. Okay, this is the origin of thermoelectric EMF. Why? How the EMF is generated in Seebeck effect? What is the relation between the potential difference and the voltage developed? We will see the relation. This is alpha into T2 minus T1, where the potential difference is equal to alpha means this is Seebeck coefficient. This is called Seebeck coefficient. So alpha is Seebeck coefficient. Alpha can be written as alpha b minus alpha a. That means in a two material closed loop circuit, if you consider the Seebeck coefficient of material A and alpha b is the Seebeck coefficient of material B, just we have seen in the previous diagram. So the difference of the two Seebeck coefficients and into the difference of two temperatures gives the value of voltage, the potential difference in a closed loop made of two different materials, and the junctions of two materials is maintained at a temperature difference, and the junctions A and B are maintained at T1 and T2. This is where, see, this formula is the mathematical relation of Seebeck effect when we consider a closed loop because of two materials. Okay, next we will see what is thermoelectric coefficient. Thermoelectric coefficient, just we have seen it is represented with alpha, and we will see the definition of thermoelectric Seebeck coefficient. Okay, the Seebeck coefficient is nothing but thermo power. Thermo power is also represented with Seebeck coefficient. What is thermo power? See, the ability of a material to generate the potential difference, how much potential difference it will generate in the material. Okay, because of the temperature difference, that means the gradient, temperature gradient, that means the temperature difference. So the actual definition of Seebeck coefficient is, see, the magnitude of voltage developed across a resistive material like metal when a 1 Kelvin of temperature difference is maintained between the 2 points of that material. Okay, suppose if you take a material and there are 2 points A and B where the temperature gradient is, the difference is 1 Kelvin 1 K between these 2 points, and the voltage, the magnitude of voltage developed across these 2 points is the Seebeck coefficient, the definition of Seebeck coefficient. So mathematically it can be represented as alpha is equal to delta V by delta T. See, this is the change in voltage when the temperature is also changing. That means if you consider the temperature difference is 1 K, what will be the change in potential difference across the 2 points. So this is the units of the Seebeck coefficient is volts per Kelvin, or we can say microvolts per Kelvin. Okay, and if the temperature difference, this is the difference and this is the voltage difference, then in another form we can also write this as E by gradient, temperature gradient. This is the electric field developed across the material because of the potential difference, because of the current flow in the material. Some electric field is developed. So how much the electric field is developed due to the temperature difference across the conductor. So these are the two representations of Seebeck coefficient. Okay, so what is the thermo power is all about? Thermo power of a material is called the efficiency of that material to create the voltage, the higher voltage, how much voltage it creates and how much it reacts to the temperature difference. Okay, this is the thermo power of a material. So how the what is the uses of the thermo power? If a thermo power, the Seebeck coefficient is high for a material, that means for a small temperature change also we will get some higher voltages. So naturally we want to get higher voltages for a small heat energy, for a small temperature differences. That means if we get higher potential differences, we will generate more power. So we can generate the more power. So in this way, if we consider an industrial purpose, materials with high Seebeck coefficient or high thermo power are very useful in generating the power from the potential differences developed across the materials. So high thermo power materials are so much of use in the industrial level. So this is all about the Seebeck effect, and next we have discussed the origin of thermoelectric EMF, and after that the Seebeck coefficient. Okay, so in the next topic we will discuss Peltier effect and Thomson effect, and we will move to further topics in thermoelectricity. Okay, thank you.